Okay, today we're going to look at another standard configuration of an operational amplifier. And the one that we're going to look at is the non-inverting operational amplifier. And remember, this is on those chips, so if you connect the resistors and sources up in this way, then it will operate as a non-inverting operational amplifier. And how we connect it up is like this. So we've got our operational amplifier, we've got the inverting input and the non-inverting input. We've got a resistor which we'll call R1. And then we've got a feedback resistor which we'll call R2. This is our V out. And then this is connected, the non-inverting input is connected to a voltage source. And we'll just call that V in. And that voltage source is connected to ground. And this resistor, this part of the circuit, is also connected to ground. Okay, so let's call the current flowing here I1, and the current flowing here I2, and the current flowing into the inverting input we'll call I minus, and this voltage here at the inverting input we'll call V minus. The voltage at the non-inverting input we'll call V plus, and the current going into the non-inverting input we'll call I plus. Okay, so remember what we said last time is that the two most important rules about an operational amplifier is that no current flows into the operational amplifier, because at the input it looks like an infinitely big resistance. And so we know from our basics of operational amplifiers that I minus, the current going into the inverting input, is equal to I plus, the current going into the non-inverting input, and those are both equal to 0 amps. Okay? And then we also know, remember, that the other job that the operational amplifier does is it tries to keep the voltage at the non-inverting and the inverting input the same. So we also know that V minus is equal to V plus. And in this case, you can see that V plus is connected here to V in, right? So we know that V minus is equal to V plus, and that's equal to V in. Okay, so those are the things that we already know about the circuit. And what we want to do is we always want to find the output voltage, V out. And we want to find it in terms of the quantities we know. So usually we know what V in is, and we know what the values of those resistances are, okay? So at this node here, because I minus is equal to 0, no current flows into the operational amplifier, we know, therefore, that, so we can say since I minus is equal to 0 amps. Therefore, I1 is equal to I2, right? And now we can use Ohm's law to express I1 and I2 in terms of voltages and resistors. So I1 we can write as, so it's flowing in this direction, in that direction, like this, and the current through a resistor flows from the higher to the lower voltage. So the lower voltage, the higher voltage here is 0. It's connected to ground, right? So I1 is equal to 0 volts minus V minus divided by R1. And that's equal to I2, which we can write as V minus minus V out divided by R2. Okay? But remember that V minus is equal to V plus is equal to V in. So we can write this as minus V in over R1 is equal to V in minus V out over R2. And then if we multiply both sides by R2, so we multiply by R2, then we get minus V in R2 over R1 is equal to V in minus V out. And so we want to express V out in terms of R1, R2, and V in. And so if we do that, we get, V in plus V in R2 over R1 is equal to V out. And so therefore, V out for a non-inverting operational amplifier is equal to V in times 1 plus R2 over R1. Okay, and remember that the relationship between the input voltage and the output voltage, that is the gain. So for the non-inverting operational amplifier, this factor here, this is the gain. Okay. Everyone happy with that? Yes? That makes sense? Okay. So, in other words, we can say that the gain of an operational amplifier is the relationship between V out and V in. And so for the non-inverting operational amplifier, the gain, therefore, is equal to 1 plus R2 over R1. Okay, everyone happy? Right, so let's do an example. So I'm going to do an example. And this is an example of a circuit using an operational amplifier. And our circuit looks like this. It's got a 0.5 volt voltage source, 0.5 volts. And that is connected to a 2 kilo ohm resistor. And that 2 kilo ohm resistor is connected to the non-inverting input of the operational amplifier. There we've got V out. We have a feedback resistor of 9 kilo ohm here. Oh, okay. And that's connected to the inverting input. And then we've got another resistor here of 1.5 kilo ohm. And that's connected to ground. And this part of the circuit with the source, that's also connected to ground. And then it is connected to a, sorry, let me just write this like this. So that I have some space. And over here we've got a 4 kilo ohm resistor. Okay, so I have labeled these things. The current here I've labeled I1, and the current here I've labeled I2. And then using the naming conventions that we've used so far, this current flowing into the non-inverting input of the amplifier is, we're going to call I plus, and the current flowing into the inverting input we're going to call I minus. And then you can see this is V plus, and this here is V minus, right? Okay, so remember the things that we always remember about operational amplifiers is we know that I plus is equal to I minus is equal to 0 amps. And we know that the operational amplifier keeps V plus equal to V minus. And we want to find out what V out is, all right? Okay, so we can do it in 2 different ways, and I'll show you hopefully that both ways give you the same solution. Okay, so the first way is to do it from first principles, right? So we can see because I plus is equal to 0 amps, so no current is flowing in here, so all the current that flows here also flows down there, right? So we know that since I plus is equal to 0 amps, therefore I1 equals I2. And now we're going to do what we did before. We're going to express those in terms of those currents, in terms of Ohm's law, and we're going to use the voltages and the resistances. So I1, you can see the current is flowing in this direction from the higher to the lower voltage, and the higher voltage is the voltage of that voltage source. So it's 0.5 amps. So I1 is equal to 0.5 volts minus V plus divided by 2 kilo ohm, and that's equal to I2, which we can write as V plus minus 0 volts, because it's connected to ground over here, divided by 4 kilo ohms. And so if we multiply this on both sides by 4,000, we get 1 minus 2V plus is equal to V plus. So therefore, 1 is equal to 3V plus. So V plus is equal to 0.33 volts. Okay, remember we know that V plus is equal to V minus, so we know that V minus over here is also equal to 0.33 volts. And we can see, I'm going to call these currents, we're going to call this I3, and we're going to call this I4. And then again, remember we know that I minus is equal to 0 amps. So we know that all the current that's flowing here is also flowing over here. Okay, and just remember, when you do analysis of operational amplifiers, although the current flowing in here is 0, the current here is not 0. Okay, so you can never assume that the current over here is 0 amps. Okay, there is some current flowing there. So we can see, since I minus is equal to 0 amps, therefore we know that I3 is equal to I4. And we're going to do the same thing again. We're going to use Ohm's law to write I3 and I4 in terms of the voltage and the resistance. So we can see in this case I3 is V out minus V minus divided by 9,000 ohms. And that's equal to I4, which is V minus 0 volts divided by 1,500 ohms. And we know that V minus is equal to 0.33 volts. So we can write this as V out minus 0.33 divided by 9,000. And that's equal to V 0.33 divided by 1,500. And so if we multiply through by 9,000, we get V out minus 0.33 is equal to 6 times 0.33, and therefore V out is equal to 1.98 plus 0.33, which is equal to 2.31 volts. And now I'm going to show you that if you just use the information that you know about the standard configuration for an operational amplifier, you can see here our non-inverting operational amplifier is connected, the non-inverting input is connected to some voltage. And that voltage in this case is created by the circuit elements that we have over here, the 2 kilo ohm, the 4 kilo ohm, and the 0.5 volt source. And that gives us a voltage over here. And then also connected to the inverting input in a non-inverting amplifier configuration, we have a feedback resistor, and then that resistance R1 that's connected to ground. Okay, so remember we said that for the for a non-inverting operational amplifier, we know that the relationship is given by V out is equal to V in times 1 plus the feedback resistor divided by R1. Okay, and we can just use that. But remember, if you use the standard configurations in a test and exam, you have to be really, really sure that you're choosing the right configuration, because it makes the solution really easy. But if you choose the wrong configuration, your answer is wrong. Then you just get 0. Then it's better to do it from first principles, like the way I did it on the left-hand side. But if we use the standard configurations, now we need to find V in, which is the voltage over here. And we can do that by using a voltage divider. So we say by voltage divider rule, we know that V plus is equal to 0.5 volts times 4 kilo ohms divided by the 4 kilo ohms plus 2 kilo ohms. Okay, because there's no current flowing in here into I plus, this piece of circuit here, this acts as a voltage divider. Okay, so this is a voltage divider. Okay, and so the result of that, as before, is 0.33 volts. Okay, so you can see on this side we found V plus in a different way, and we did it in this way, and here we did it using the voltage divider, and both give us the same result. And now we're going to use the standard configuration for an non-inverting operational amplifier. So we know that V out is equal to V in, and V in is, in this case, 0.33 volts, and that is multiplied by 1 plus RF, which is 9,000, over R1, which is 1,500, and that gives us 0.33 times 7, and that is the same as we had before, so it's 2.31 volts as before.